Okay, this video is just going to talk about the few examples that were given at the very end. I just wanted to make sure that I touched on some of these because I did it with everybody else. So let's see. The first question that I want to talk about is 26 and 27. So we talked about so far all the things that we've been doing are uniform circular motion. Uniform circular motion means the radius stays the same and the object travels at a constant velocity. But this problem gives you an example of a race car starting from rest in a pit area and accelerates at a uniform rate to a speed of 35 meters per second. So when you're reading through this problem, you notice, I wonder if this is going to write. Oh yeah, you notice that it has an initial velocity in the x direction. I don't even know if I want to call it the x direction, and a final velocity in the x direction, as well as a time. And if it has all three of those things, we know there's an acceleration. The acceleration, though, is tangential acceleration, which is different than centripetal acceleration. So I have an object that's traveling in a circle. If it's traveling in a circle with a constant radius, it has radial or centripetal acceleration. We know that because we've done that so far. However, if the object's not going at a constant velocity around in the circle and it's speeding up or slowing down, it also has tangential acceleration. Tangential acceleration means that it is non-uniform accelerated motion, meaning the acceleration is changing tangentially as well as centripetally. So this problem, and tangential acceleration is just kinematics like we've done before. Centripetal acceleration is what we are doing in this unit. So you will treat tangential acceleration like traditional kinematics. Radial acceleration is the same as centripetal acceleration, and you'll do that with centripetal acceleration equations. Similarly, 27 goes along with it. It's just having you change some values. 28, we already talked about a centrifuge. We did this problem together in class, but I just want you to know the equations that we have dealt with, or the equations that you just put on that sheet, on the back side of that sheet. Each of the ones that are boxed equations have different things we're solving for, different things the question asks for. So there's two main things that the question will ask for. It will ask for a gravitational force, which is a force of gravity. The main equation is that first boxed equation on the sheet that we were just going through. If they ask for so like this one, this says what is the force of gravity? So they're asking for force of gravity. You're using that first equation on that equation sheet. When it asks for something else, find the net force. So again, net force, this is a different problem, but I want to come across one where they're asking for something else. Acceleration due to gravity. So acceleration due to gravity, or gravitational field strength, those are little g values, not F sub g. That's a force that has units of newtons. It's a force. This is an acceleration, or gravitational field strength. It has units of meters per second squared. So you just have to kind of think about, so this problem right here, number 32, would be using the fourth equation down, the little g equals big G m over r squared. So just make sure that you're using the appropriate equation based on what they're asking, because the wording is very similar. Asking for an acceleration due to gravity is not the same as asking for a gravitational force, or the force of gravity. They sound similar, but they're not. This question, this is actually a really easy question. It looks a lot more complicated. It gives you a theta, like when have we ever dealt with thetas? It's not necessary. Basically, you are finding the force of gravity between the moon and the earth using that first equation on the equation sheet we just wrote. Then you're also finding the force of gravity as a separate problem between the moon and the sun using that first equation, two separate forces. And then this is nothing different than vectors. If you have two vectors pointing at a right angle, you're basically just finding the hypotenuse. So a squared plus b squared gives us the net force. The moon is feeling a force from both of these things, and together you sum those forces just by using Pythagorean theorem. Geosynchronous satellites. Actually, this is kind of an important one that we talked about. Geosynchronous satellite is one that stays above the same point on the Earth, which is usually the equator, such that a Satellites are used for TVs and radio transmission, weather forecasting, and so on. Determine the height above the Earth's surface such that the satellite must orbit. So if they're asking for the height above the Earth's surface, they're asking for the radius, or the distance from the Earth's surface to up where that satellite is at. But remember, that includes when we solve for radius. So this is going to those equations that we just derived off to the side. Radius is equal to cube root of blah, 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 whatever was on the inside of it. This radius that you're solving for here is not just the radius of the Earth, but the height of the satellite. So be sure if they're asking for the height above the Earth's surface that you solve for radius and then subtract from it the actual radius of the Earth to find the height of the satellite, you know, if there's some satellite up there. And the only thing you might be a little bit confused about, which everybody else was, in this equation it is big G m2 period squared over 4 pi squared. We can find the mass of the Earth. That's pretty easy. 4 pi, big G. We know all these. The period of a geosynchronous satellite is 1 full revolution around the Earth. So it's 1 rotation of the Earth. So it's 24 hours. But of course, we have to put it into seconds. And then they ask you for speed. Of course, we have an equation for satellite speed. We put that at the bottom. And then compare the speed of a satellite orbiting 200 kilometers. So try these problems. Try the complicated equations. One thing I told everybody is it's very standard to go through these problems and get them wrong because there's a lot of big numbers. There's a lot of things to mix up accidentally. You know, you're going to use the radius of the Earth on the back side of that paper to help you with this problem specifically. You don't need to memorize those values. They should be provided for you, but they are just helpful, I feel like, when you're working through the bookwork. This is a Kepler's law, so this is just helping you to practice with that Kepler's law equation. Sun's mass, determine the mass of the sun given the Earth's distance from the sun. So again, if we're solving for a mass, think about equations that have mass in it, and they're asking for the mass of the sun. And they're saying given that the Earth's distance from the sun, so we have the Earth as an object, we have the sun as the central body, and we have the distance between these things. So think, what's the force that's acting on these two objects? What's the force that the sun is exerting to pull the Earth toward it? Well, it's the force of gravity, and that force of gravity is a centripetal force that's pulling it in that circular motion around it. Remember, when we get this down far enough, our central body, our rotating body cancels out. This is big G m1 m2 over r squared. This is m times centripetal acceleration, but m1 would be our Earth, m2 would be our sun. So this is m1. So m1 would cancel out. The mass of the Earth doesn't matter. The mass of the sun is the central body. That's what they're asking for in the problem. You may need to go farther with this because we have the radius. We don't know the centripetal acceleration, so you have to break this down a little bit farther into v squared over r, and then you have to break down v a little farther into 2 pi r over t, and use the period as 1 revolution of the Earth around the sun. So you'll have to do a little bit of math, 365 days, convert it into seconds, but all of these problems require you to do like a lot of thinking about orbiting bodies. Question 36, let me see, I've lost kind of track. I would suggest going through all these problems, check as you go. Again, this one's asking for what's the force of the Earth's gravity. What's the force of gravity? So you're probably going to be using that first equation. Force of gravity is big G m1 m2 over r squared. Given the acceleration of gravity on the Earth's surface, at the surface of Mars is 0.3 of what it is on Earth. So basically that's saying 0.38 times little g is what Mars's gravity is. So, I wouldn't put it like that. That doesn't make sense. Little g is 0.38 times what it is on Earth, 9.8. So that's the acceleration due to gravity. Determine the mass of Mars and the radius. So again, I'm going to look at an equation that has little g in it. Little g is big G, m of the central body is Mars, over r squared. That's the distance from an object that's standing on Mars is from the center of Mars, which is the radius, which is what they give you. And then I just suggested for everybody to do these last few problems, solving for whether it's the acceleration due to gravity, which is little g, or the force of gravity, which is F sub g, gravitational force. So try those last few problems, know that the answers are online, and let me know if you have any questions.